Every single day, without anyone noticing, the top of the Eiffel Tower moves, not because of the wind, though wind moves it too. This movement is slower, stranger, and more reliable than any gust. Over the course of a sunny day, the summit of the Eiffel Tower quietly drifts in a small circle, leaning away from the sun as it crosses the sky, then swinging back again as the day cools, morning, noon, evening. The tip of one of the most famous structures on Earth traces a path through the air roughly the width of a dinner plate, and then returns and does it all again the next day. The 7,000 tons of iron standing over Paris are not as still as they look. The tower is alive with movement, leaning, stretching, shrinking, bowing, all in response to nothing more than the temperature of the air and the position of the sun. In a real sense, the Eiffel Tower is not just a monument. It is the largest thermometer in the world, and it has been silently taking the temperature of Paris for over 130 years. Tonight, we are going to work out why. Why a giant iron tower cannot hold still. Why it leans away from the sun instead of toward it. Why it is taller in summer than in winter, and why almost everything you have heard about exactly how much taller is wrong, and why the same invisible force, the one gently rocking the Eiffel Tower, is one of the most important and dangerous things that every engineer who builds anything large has to defeat. It all comes down to a single, simple fact about the physical world, one you have felt but probably never thought about. Almost everything gets bigger when it gets hot. Let me explain what is actually happening because it starts at a scale far too small to see. Everything around you is made of atoms, and those atoms are never truly still. They are always vibrating, jiggling in place, and when you add heat to a material, you are really just making its atoms vibrate harder. The more they vibrate, the more room each one needs, and the farther apart they push from their neighbors. Multiply that across trillions upon trillions of atoms, and the whole object grows, not by melting, not by changing, simply by warming. Its atoms are dancing a little more wildly, and so the material swells. This is called thermal expansion, and it is one of the most universal behaviors in nature. Heat something, it expands. Cool it, it contracts. A metal lid on a glass jar loosens under hot water because the metal expands faster than the glass. A road buckles in a heat wave, and a 300-meter iron tower in Paris gets taller in the summer sun. Now, iron in particular expands a very specific, predictable amount for every degree it warms. For a small object, this is far too tiny to notice. But the Eiffel Tower is not a small object. It is over 300 meters of iron. And when you stack up that expansion across 300 meters of height, even a tiny stretch per meter adds up to something real. So here is where we have to be honest, because this is the exact point where the internet gets the story wrong. Spectacularly wrong. You have probably seen the claim, repeated endlessly online, that the Eiffel Tower grows about 6 inches, some 15 centimeters taller in summer than in winter. It is one of those facts that gets shared on every list of amazing trivia, and it is not true. Fact-checkers have traced the real numbers, and the actual change in the tower's height between a cold winter's day and a hot summer's day is only a matter of millimeters, a few small millimeters, not 15 centimeters. Paris simply does not swing between hot and cold enough to stretch the iron by half a foot. The height change is real, but it is small, and you would need precise instruments to measure it. So where did the 15 centimeters come from? It is not invented, it is a real number, but it describes something completely different. And that something is far more interesting than the height ever was, because the tower does not just grow, it leans. Here is the key insight that the trivia lists miss. The sun does not heat the whole tower evenly. At any given moment on a sunny day, the sun is shining on one side of the Eiffel Tower, the east side in the morning, the south around midday, the west in the afternoon. And the side facing the sun gets hot. The 3 sides in shadow stay cooler. Now think about what thermal expansion does to that. The hot, sunlit side of the tower expands more than the cool, shaded sides. One face of the tower is stretching while the others hold still. And when one side of a structure grows longer than the other 3, the whole thing has no choice but to bend. It curves away from the side that is expanding. The tower leans away from the sun. And because the sun moves across the sky through the day, rising in the east, arcing across the south, setting in the west, the hot side of the tower moves with it. So the direction of the lean travels around the tower over the course of the day. In the morning, the tower leans west, away from the rising eastern sun. At midday, it leans north, away from the high southern sun. In the evening, it leans east, away from the setting western sun. The summit, following this shifting bow, traces out a slow circle in the air, and that circle is roughly 15 centimeters across. There is your 15 centimeters. It was never the height. It was the width of the daily circle, the traveling sun. Someone, somewhere, mixed up the lean with the height, and the mistake has been copied ever since. The truth is stranger and more beautiful than the myth. The Eiffel Tower is not so much growing as it is bowing, gracefully all day long, always turning its lean away from the sun like a sunflower doing the exact opposite. And this is why it is fair to call the Eiffel Tower a giant thermometer. Its height and its lean both track the temperature and the sunlight falling on it, moment to moment. If you could read its exact position precisely enough, you could work backwards and tell how warm it was and where the sun was in the sky. The monument is quietly, constantly reporting the weather, written in the language of expanding iron. Now, here is the part that lifts this from a piece of Paris trivia into something that matters. The force gently rocking the Eiffel Tower is not a cute quirk of one famous landmark. It is a relentless, powerful enemy that every large structure on Earth has to be designed around. And if engineers ignore it, it does not politely nudge things a few millimeters. It rips them apart. Consider a steel bridge. On a hot summer day, the steel in a long bridge expands significantly. A bridge hundreds of meters long can grow by a noticeable fraction of a meter between a freezing winter night and a baking summer afternoon. Now the bridge is anchored at its ends, so what happens to all that expansion? The material has to go somewhere. If the bridge were locked rigidly in place at both ends with nowhere to move, the force of that expansion would build up inside the structure with enormous power, buckling the roadway, cracking the supports, tearing the bridge apart from within. Thermal expansion, contained, becomes a crushing force. So engineers do something clever. They leave gaps. If you have ever driven across a large bridge and heard a rhythmic thud, thud under your tires, you have crossed expansion joints. Deliberate gaps built into the structure, often with interlocking metal teeth, that let the bridge grow and shrink freely without tearing itself apart. Those gaps are not sloppy construction. They are precisely engineered room for the bridge to breathe as the temperature changes. In winter, the gaps are wide. In summer, as the steel expands, they close up. The bridge is designed from the start to move. The same is true of railway tracks. Older rails were laid in segments with small gaps between them. That classic clackety-clack of a train is partly the sound of the wheels crossing those gaps, which existed to give the steel room to expand. Leave no gap, and on a hot enough day the rails can push against each other with such force that they buckle sideways, twisting the track into a snake of steel that can derail a train. Engineers have watched it happen. Heat alone, with nowhere to go, can bend a railway line like a piece of wire. And it goes on. Everywhere you look, once you notice, see it. The gaps between sections of concrete on a motorway. The strange sliding joints in the pipes of an oil refinery. The way tall buildings and long pipelines are built with flexibility to absorb the daily and seasonal swelling and shrinking of their own materials. All of it is a quiet, constant negotiation with thermal expansion. The same force, the very same physics, that makes the Eiffel Tower lean away from the sun. To feel just how powerful this force becomes at the extremes, consider a few examples that push it to the limit. The Concorde, flying at more than twice the speed of sound, heated up so much from the friction of the air rushing past it that the entire aircraft stretched. The fuselage grew by as much as 10 inches in flight, then shrank back on the ground. Pilots reported a gap opening up on the flight deck as the plane expanded, wide enough to slot an object into, that would then slowly close again as the aircraft cooled after landing. That is thermal expansion made visible in real time at the scale of an entire aircraft. Or consider what happens when it is ignored. Railway lines around the world buckle every summer during heat waves, the steel expanding with nowhere to go until the track kinks sideways, and services have to be stopped before a train derails on the twisted rail. Long steel pipelines crossing deserts have to be laid in deliberate zigzags rather than straight lines, so that when the sun heats them, the pipe can flex at the bends instead of tearing itself from its supports. Bridges have been known to seize and crack when their expansion joints clogged and could no longer move. In every one of these cases, the villain is the same gentle force that merely rocks the Eiffel Tower, But unleashed on a structure that was not designed to accommodate it, it becomes a wrecking force strong enough to bend steel like wire. The difference between a graceful lean and a catastrophic buckle is entirely down to whether the engineer planned for the movement. Eiffel planned for it, and so his tower bows and survives, while a rigid structure that denied the same force would tear itself apart. The reason the Eiffel Tower shows it to us so gracefully is that Gustav Eiffel and his engineers understood this force perfectly. It is worth pausing on just how far ahead of his time Eiffel was, because this was the 1880s, long before computers, long before modern engineering software. When Eiffel's team designed the tower for the 1889 World's Fair, they were building the tallest structure humanity had ever made, more than 300 meters of iron, nearly double the height of anything that had come before. And they had to account, by hand, with pencil and paper, for every force that would act on it. The crushing weight of the iron itself, the pressure of the wind, and, yes, the daily and seasonal expansion and contraction of the metal as the temperature changed. Eiffel's calculations deliberately allowed for thermal deformation. He knew the sun would heat one face more than the others. He knew the tower would lean. He designed it to do so safely. And that is the secret hiding in the tower's famous shape. That open, airy lattice of crisscrossed iron, the look that makes the Eiffel Tower instantly recognizable, is not just for beauty, it is structural genius. An open lattice lets the wind pass through instead of pushing against a solid wall. It uses far less iron than a solid tower would, keeping the whole thing lighter. And critically, it gives the structure the flexibility to flex, sway, and bow without stress building up in any one place. The tower's elegance and its survival are the same thing. Eiffel did not build a rigid monument and hope it would resist the elements. He built a flexible one, designed from the first sketch to move with them. The graceful shape you admire is the visible form of an engineer who understood, more than a century ago, that the way to defeat these forces was not to resist them, but to bend with them. When they designed the tower in the 1880s, they knew the iron would expand, contract, and bend with the heat and the wind, and they built a structure, that elegant, open lattice, curved and tapering, that could flex and breathe and lean without any harm at all. The tower is not fighting the movement, it is designed to move. It sways in the wind, bows in the sun, grows in the heat, and shrinks in the cold. And it has been doing so, safely, every single day for well over a century. So the next time you see a picture of the Eiffel Tower, standing there looking eternal and unmovable against the Paris sky, remember what is really going on. That iron is not frozen. At that very moment, the sunlit side is warmer than the shaded sides, and the whole tower is leaning, ever so slightly, away from the sun. Its summit is sitting a few centimeters from where it was at dawn, tracing out its slow daily circle in the air. It is a fraction taller than it was last winter, and it is, in its own silent way, telling anyone who knows how to read it exactly how warm the day is. We build monuments to last forever, to stand still against time. But the Eiffel Tower teaches a quieter truth. Nothing that large is ever truly still. Even iron breathes. Even a monument moves. And the same invisible force that would tear a bridge apart if we ignored it is, in Paris, expressed as something close to grace, a giant iron tower leaning away from the sun, all day, every day, for as long as the sun keeps crossing the sky. The Eiffel Tower does not stand against the world. It moves with it, and that is exactly why it is still standing.